So in this video we're going to look at graphs of logarithmic functions. We're going to look at the graph itself and its key points. We're going to look at the effect of the size of the base on the shape of the function, and then we're going to go back to our transformation pattern and we're going to look at transforming log functions, including looking at how you find x-intercepts, y-intercepts if they exist, and then determining the domain. So for our graphs of logarithmic functions, we have two basic shapes and they are determined by the size of the base. So in the first one we've got log to the base a of x, and our a value is a positive value greater than 1. And so the general shape of the graph looks like this. It has an asymptote at x is equal to 0, and it has a couple of key points. It passes through the point 1, 0, so it has an x-intercept of 1, and when y is equal to 1, the x value is in fact a. So that point here has coordinates a1, and the point down here has coordinates 1 on a minus 1. When your base is between 0 and 1, for example log to the base of a half x, what you get is the same shape as before but reflected across the x-axis. So this shape here and this shape here are the same shape, just reflected across the x-axis. And then what you get for your key points, this is now a minus 1, and this point now will be 1 on a and 1. So it's important that you recognize the two different shapes of the graph based on the size of the base of the function. So changing the base value itself, not just whether it is between 0 and 1 or greater than 1, but changing the base value itself can actually also change the position of the log graph. So what's the difference between log to the base 2 of x and log to the base 10 of x? What happens there? So I have a Desmos example set up here, so let's play this example. And so what I've got here is I have log to the base of a, and I have a slider for a, and you can see that a is increasing, and you can see the change in the shape of the graph. So as a is 2, 3, 4, 5, 6, 7, 8, can you describe how the shape of the graph is changing? So let's look at it just again. So what we're seeing here is for values of x that are greater than 1, as the a value gets larger, it's tending to move down this way, it's becoming flatter. And if we look here in this little section here, as a gets bigger, it's kind of pushing in towards 0, 0. So as the size of the base gets bigger for x values greater than 1, so for these x values here, it becomes flatter for those x values there. For values between 0 and 1, which is those x values there, the graph actually moves towards 0, 0. So that's what happens for graphs where your base is greater than 1. Let's now have a look at the graphs where our base is between 0 and 1. So I have the same setup with Desmos. However, this time I've got my slider going between 0 and 1. So when it's a base of 0, we've got log to the 0, which you can't have. You have to have a positive number here. And we want it to go from 0 up to, but not including 1. So when we get to 0 and 1, it disappears. So let's play this and watch what happens to the shape of the graph as the a value gets larger. So there's our generic shape, and as you can see, as the a value is getting larger and larger, what's happening? What's happening to the shape of the graph? So this bit here is moving towards the line x is equal to 1. This bit is moving away from the x-axis. So that seems a little bit counterintuitive as to what we noticed for the bases that are greater than 1. So let's have a look at them combined together. So in this Desmos setup, I've got log a to the x. I've got the line y is equal to 1 so that you can see how it's bending down relative to y is equal to 1. And I've got the a value going from 0 to 3. It's currently set at 1.9, which is greater than 1, so that gives us this particular shape here. And so when I press go, it's going to increase itself up to 3, and then it will flick back and start at 0. So I'll talk you through it, you watch it, and I'll talk you through the values of a. And there we go, 1.8, 1.9, 2. 2.2, 2.4, 2.6, 2.8, 3, 0, 0.2, 0.4, 0.6, 0.8, 1, 1.2. Can you see a pattern to how it's moving? It's kind of twisting and rotating around the point 1, 0. It's twisting and rotating around this point. Watch it. Here it goes. This bit's moving this way, and the other bit was moving that way. But it's always stopping at that y-axis as it twists around. So as a increases from 0, it starts off in this shape, and then it flexes around, pivots around that point there. So this goes that way, and that goes that way, that goes that way, and that goes that way, until it stops at the barrier of the y-axis. Did I say x-axis before? I meant y-axis. So that's the pattern in the shape of the graph as the base changes. So now we're going to have a look at transforming the log function using this format here, where we've got our dilation and reflection on our y values at the front. We've got log to some base that we know changes the shape, but we're not going to worry about that at the minute. We're just going to look at the normal transformations. So our y transformations and our x transformations. So I have a Desmos set up here. Hopefully this will allow me to play. You can see that I have y is equal to a log n x plus b plus c set up here, and I've got some sliders for the value of a, b and c. And the dotted green line is the y is equal to log of x, just for a reference to see what happens. So now I'm going to change the value of a and watch what happens. So as a increases, you can see the graph moving, dilating away from the x-axis. You see that dilation stretching that way? If I bring it back down, it's getting closer and closer to the x-axis until it becomes negative, and now it's flipped it over. See the reflection? Now it flips it over the other way, and as it becomes more negative, it stretches it further away from the x-axis. So that's exactly the same as what's happened for all of our other graphs. So if I set this back to about 1, go to 1. Now I'm going to play with the n value, which is the dilation by a factor of n from 1 on n from the x-axis. So what it looks like it's doing, it's actually dragging it in and out from the y-axis, but it looks like it's moving up and down because you can't actually see it stretching or compressing in or stretching out. And so you get this particular shape, but when I turn it to negative, you'll see it flip across. There it is there. So if you focus on the x-intercept, you'll see that as the n value gets larger, the x-intercept moves closer and closer to 0, 0, which is what we expect. So I'll put this back at 1. Sit there. Our b is our horizontal translation, and let's see what happens when we change this. So I'm currently making it +3 +4, 2, 1, +1, 0. Now the b value is -1, -2, -3. So it does exactly the same as it has done for all our other functions. And the plus c on the end of the formula at the top shifts the whole thing up and down. So these particular transformations do exactly the same thing for log graphs as they do for all of our other graphs. So let's have a look at using transformations to sketch a log graph. So let's look at sketching y is equal to -2 log to the base e of 2x plus 3 plus 1. So the first thing we've got to make sure is that it's in the correct format, so that our coefficient of x should be a 1. And in this case it's not, so we need to take a common factor of 2 out of this bracket, and then we end up with 2 brackets x plus 3 on 2. And now we can read our transformations off. So -2 tells us that it's reflected in the x-axis, so it's flipped this way, and dilated by a factor of 2 from the x-axis, so it's stretched this way. So overall our shape looks like this. Our dilation factor by 1/2 from the y-axis just squishes it in towards the y-axis. You can't really see much of a change of the shape overall, so for a sketch we're not going to worry about that too much. The +3 over 2 is our translation left 3 over 2 units, which basically tells us, if we look at where the asymptote was for our original function, which I'm just popping in on the other graph over here now, it was x is equal to 0. So if it's translated left 3 on 2 units, now our asymptote is at x is equal to -3 on 2. So these two bits here we can use to help us to position the graph correctly when we sketch it. We also know it's gone up 3 units, up 1 unit. So let's have a look. To be able to sketch this properly, what we need to know is, does it cut, given that it's over here, the asymptote is over here, and the shape of the graph goes down this way, it's either going to have a positive or a negative y-intercept, or it will have either a positive or a negative x-intercept. So the only way to find that out is to find the x-intercept and find the y-intercept, and then we can sketch it. So let's do that. So let's find the x-intercept, and while we're at it we may as well talk about an implied domain, because that comes up in some questions as well. But let's go with the x-intercept. Find the x-intercept, you let y equal to 0. So in our equation we put 0 for y, and then we solve for x. So -1 from both sides to get rid of the +1. Divide both sides by -2, and you end up with -1 divided by -2, which gives you 1/2. What I'm going to do now with this log equation is I'm going to rewrite the log equation as its equivalent exponential equation. So our base is e, our power is 1/2, and the value is what we're finding the log of. And now I can rearrange this equation to get x by itself. So -3 from both sides, and then divide both sides by 2, and I get x is equal to 1/2 outside of e to the 1/2 minus 3. So that's a very strange number, but where is actually that on the x-axis, and how do I go about finding that out if I don't have my CAS calculator? So what we actually do is we use what we know about square roots. So let's have a look at this. So we know that x is equal to a half outside of, now e to the half is in fact the square root of e, take away 3. So all we need to figure out is it a positive number or is it a negative number? So we're going to say x is approximately a half times the square root of, now e is 2.7. So we need to figure out, is the square root of 2.7 minus 3 a negative number or not? So what we do is we look at the perfect squares either side of 2.7. So we know the square root of 1 is 1. We also know, these are our perfect squares, the square root of 1 is 1 and the square root of 4 is 2. So the square root of 2 will be somewhere in between those two numbers. So on a number line, you can see that the square root of 1 is 1 and that the square root of 4 is 2. So somewhere in between here is the square root of 2 and the square root of 3. And in between the square root of 2 and the square root of 3 is the square root of 2.7, which is the square root of e, somewhere in here. So what we've got for the square root of 2.7 is a number that is between 1 and 2. In fact, if you work it out in your CAS calculator, it's 1.65. But what we need to take notice of is that we have a small number and we are subtracting a larger number in 3. And so, larger. And so what you end up with is a negative number. Let me say that again. So this value is smaller than this value. So if you had a small number, take away a large number, you end up with a negative number. So we've got that our x value, our x-intercept, is in fact a negative number. So we can go ahead and put up on our graph up here, we can put a dot somewhere in the negative section. Now for our implied domain, or for our domain of our function, we know that the shape of the graph is this shape, that curved shape like that, and so we just put it in here. So our implied domain is, we can't have our asymptote, but any value greater than our asymptote is our implied domain. So you can either do it using the value that you're finding the log of, the expression that you're finding the log of as being greater than 0, or you can say that it is to whichever side of the asymptote you need for the shape of your graph. So the only time the graph is going to flick across to this side of the asymptote is if our n value is negative. Let me say that again. So if we had an equation where we had a negative n value, so something like y is equal to log to the base e of negative brackets x plus 2, then this is the only time that our graph will flip across and be this side of the asymptote. Okay, so otherwise the domain is always to the right hand side of the asymptote. Let's find our y-intercept by finding whether our x-intercept is positive or negative. Given the shape of the graph, it's going to imply that we've either got a positive y-intercept if it's a positive x-intercept, or a negative y-intercept if it's a negative x-intercept. So let's look at that. So realistically, we already know the shape of our graph as that shape, and so we are looking for a negative y-intercept. To find a y-intercept, you let x is equal to 0. So in the equation, you put a 0 where the x is, and you tidy it up, and you're going to get this terrible expression here. It's going to be some kind of log. Because we don't have a calculator, we're going to need to leave this particular value as our y-intercept. Hopefully that will allow you to be able to sketch your own transformed log functions. There are a couple of other things that you need to know about log functions and how to sketch them. So there are a couple of videos that follow up this video. You'll find them in the playlist directly below this video.